Welcome back, everyone, to our final Masterclass Explainer. Look, you've made it through the entire syllabus of cloud, fog, and edge computing. That is huge. But right now, we need to talk about how you actually secure top marks in your end semester exam. Because if you've looked at almost every university question paper out there, you'll know there is this massive, high-stakes 15-mark section dedicated entirely to real-world case studies. And honestly, if you can't draw a clean architectural block diagram and explain the data flow for these systems, you are literally leaving major points on the table. Okay, let's dive into this. Seriously, I want you to grab your notebook right now and get ready to sketch these architectural block diagrams right alongside me. By the time we finish this explainer, you are going to have exactly what you need to absolutely dominate those case study questions and lock in those final grades. So here is our blueprint for today. We're looking at smart healthcare network design, intelligent traffic systems, smart city hierarchical scaling, and we'll wrap it all up with a rapid-fire review of high-yield previous year questions. Let's get into it. Section 1, Smart Healthcare Network Design. We're going to look at exactly why traditional cloud healthcare completely fails during critical emergencies, and more importantly, how to fix it. Picture this. You've got wearable sensors streaming raw ECG data directly to a remote cloud. Sounds great, right? Well, if a patient suffers a sudden cardiac event, just a tiny bit of network latency or a dropped Wi-Fi signal can delay that medical alert. And that delay, it can literally cost lives. Plus, streaming raw, sensitive patient data over the public internet is a massive violation of data privacy laws like HIPAA and GDPR. And this brilliantly illustrates how a three-tier architecture fixes these life-threatening flaws by dropping an e-health gateway right at the fog layer. So on your exam, you want to divide your explanation into 4 key functional responsibilities. First up, protocol conversion. The gateway translates low-power local signals like BLE into MQTT over TCP/IP. Second is local anomaly detection. A lightweight local algorithm analyzes the ECG waveform frame by frame. If it spots ventricular fibrillation, boom, it triggers an alert in under 5 milliseconds, locally, no waiting for the cloud. Third, data reduction and privacy. It filters out the noise and encrypts data using AES 256 right there at the edge. And fourth, offline autonomy, meaning even if the internet drops completely, the gateway just keeps buffering records and driving those local alarms. All right, let's transition to Section 2, Intelligent Traffic System Architecture. So, modern cities absolutely need real-time traffic signal optimization and automated accident detection. But think about the absolute bandwidth nightmare of a centralized cloud constantly trying to adjust every single traffic light for an entire city in real time. It's impossible. That's why we use multi-access edge computing, or MEC, and roadside units that act as fog nodes. Now, what's really interesting here, and what you must contrast on your exam, are 2 vital messaging paradigms. First, V2V, or vehicle-to-vehicle. This is for direct microsecond communication between adjacent cars. Think instant collision avoiding braking. On the flip side, we have V2I, or vehicle-to-infrastructure. This is how those vehicles talk to the roadside units for broader city-level traffic orchestration. Let's actually bring this abstract architecture to life with a vivid scenario you can use on your exam. Imagine an ambulance screaming towards a crowded intersection. Its onboard unit broadcasts a priority signal to the local roadside unit using cellular V2X. Because this roadside unit is an edge node, it's running a local control script that instantly switches the traffic lights to green along the ambulance's path. The absolute critical takeaway here? This whole thing happens in sub-10 millisecond latency entirely locally without ever having to ask a distant cloud for authorization. Moving right along to Section 3. Smart City Hierarchical Scaling. Smart cities deal with an absolutely extreme scale of IoT. We're talking millions of heterogeneous endpoints, everything from smart electric meters and water pressure sensors to PM 2.5 air quality monitors. You simply cannot push millions of events per second all the way to the cloud without the whole system crashing. So let's move to and see how this builds into a solution, the 4-layer hierarchical fog architecture. When you describe this in your exam, you've got to emphasize how data processing is smartly partitioned. Down at the bottom, the field layer collects raw environmental parameters every single second. Above that, the local fog layer aggregates that telemetry. So if a smart grid transformer detects a voltage surge, this local layer isolates the fault in milliseconds. Moving up again, the micro data center layer processes ward-level trends, like localized pollution spikes. And finally, way at the top, the cloud layer only receives daily summaries, and those are just used for long-term urban policy and infrastructure planning. And that brings us to Section 4, Previous Year Questions Wrap-Up. I'm taking you through a rapid-fire review of the top 5 high-yield questions, so definitely get your pens ready. Question 1 often asks you to compare cloud, fog, and edge computing.
So the crucial point is knowing exactly how to construct a clean three-column table. You want to compare them across location, latency, and swap-C constraints. Make sure you explicitly state where the computing actually happens. Edge happens right on the device with under 1 millisecond latency. Fog happens on the local network nodes at around 10 milliseconds. And cloud? That happens far away at centralized data centers, usually exceeding 100 milliseconds.
Question 2 is a classic. It asks for the architectural pillars of the Open Fog reference architecture. The absolute easiest way to secure these 10 marks is to use a simple memory hook. Scale-ROS. That stands for security, scalability, openness, autonomy, programmability, and RAS, which is reliability, availability, and maintainability. Literally just write that acronym down right now and you won't forget it. Moving on, question 3 usually asks why lightweight containers are preferred over virtual machines at the edge. Your answer really needs to contrast the two. Point out that VMs require a heavy guest OS and a hypervisor. That completely wastes memory on hardware that is strictly bound by those swap-C constraints we talked about. Containers, however, perform OS-level virtualization. They share the host kernel, which gives you millisecond boot times and a tiny megabyte-level footprint. Oh, and be sure to drop a mention of K3s as a perfect edge orchestrator. Examiners love that. Question 4 is a two-parter all about networking in fog environments. First up is SDN, or software-defined networking. Keep it simple. Define it as the technology that decouples the control plane from the data plane. That separation right there is exactly what allows for dynamic, intelligent traffic routing across really complex fog networks.
And the second half of that question is NFV, or Network Function Virtualization. You need to explain how NFV works right alongside SDN. Basically, NFV takes traditional, bulky hardware appliances, think firewalls or routers, and turns them into virtual network functions. And the best part? These functions run directly inside lightweight containers right there on the edge nodes.
And finally, question 5, drawing and explaining the eHealth Fog Gateway. Guess what? This is literally exactly what we covered back in section 1. All you have to do is replicate that 3-tier diagram and list those 4 functional roles: protocol conversion, anomaly detection, encryption, and offline autonomy. See, you already have all the tools you need to secure those 15 marks. Well, congratulations on mastering this explainer. Look, if you can draw these block diagrams and recall these comparison matrices, you are fully equipped to crush your exam, for sure. But before we wrap up today, I want to leave you with one final provocative thought. As billions, literally billions, of AI-driven devices come online in the near future, how will these edge networks need to evolve to handle entirely unprecedented levels of autonomous split-second decision-making? It's kind of crazy to think about. Anyway, keep exploring, keep questioning, and good luck on your exams. You've totally got this.